Welcome back, ladies and gentlemen. Today we're going to be continuing our discussion about solutions, and we're going to talk about solubility. Now, we spoke about solubility already in the previous videos. We talked about the nature of solubility, about how things dissolve into other things, right? We talked about how like dissolves in like. The polar bear dissolves in polar solvent. I know. Wasn't any funnier the first time. And what we're going to be seeing now is we're going to talk about solubility in a little more detail. Okay, it's just going to be a few extra pieces here and there, and some numbers, some graphs, stuff like that. So let's take a look. Solubility describes the amount of solute that will dissolve in a given quantity or amount of solvent at a particular temperature. Because as we discussed last time with trying to get things to dissolve, temperature can change things, right? Because if the temperature is very high, that means the particles are moving very fast. And if the particles are moving very fast and they hit it into each other, they're more likely to get those new connections and then pull them away. Right? And we talked about how ionic compounds can be dissolved in this manner. So temperature is pretty critical. There are three ways in which we can describe how soluble a substance is in a solution. Okay, so we got three options, which is rare. Usually we have a binary compound or a binary choice. This time we've got a trinary choice, tri meaning three. Saturated solution. Before we go any further, let's think this through. Solution, obviously that makes sense. Saturated. What does saturated mean? It's full. Basically, it means it's full. So a solution that holds the maximum amount of solute possible for that temperature. We are full. Okay, so we've got our handy basket here. How many things can I use this basket to describe? Right now, there's still room, right? I could put a few more markers in there. So I'm going to grab a couple more here. Here we go. We got some more markers. Another one. We're going to grab one of these. Maybe a couple more from over here. There we go. That is now a saturated marker box. See? We cannot put anything more in there. So this is saturated. Pretty straightforward. If you add more solute to the solution, it will not dissolve. Instead, it will fall to the bottom of the container. Okay, this is a little harder to do with a marker box, but basically what I'm saying is if I try to take another one and stuff it in here, there's no room for it. So it'll just sit at the bottom. It'll, in this case, sit on top like this, but that's because these are, of course, solids. In the case of a solution, we're usually talking about liquids, so in that case, it would sit at the bottom of the liquid. And you've seen this probably. You've probably had a situation where you've placed some kind of drink mix, for example, in water. If the drink mix is sitting on the bottom, it's not dissolving. You got to stir it up maybe to get it to finish dissolving. Well, if it doesn't dissolve no matter what you do, it is saturated. For example, if you add more sugar to a saturated solution, the added sugar will simply drop to the bottom of the container. It will be a precipitate. That is the name we give to something that has fallen out of solution and lands on the bottom. It's sort of like precipitation, like rain. It's a fancy way to say rain. In this case, it's because this particular material rains out of solution, falls out. We'll see that as we go through this. Next option, unsaturated solution. That's what we started with. This is saturated. Unsaturated is if I pull all these extra markers out, there's my unsaturated solution, right? It's got room in there. We could stick more. Awesome. Our markers, we don't need them anymore. Put them off to the side. But that's what our unsaturated solution is going to be, right? You hold less than the maximum amount of solute possible at a given temperature. Notice it says given temperature. If we change the temperature, we're going to change the solubility of the system. So the amount of markers that can fit in here depends on the temperature. So in the analogy of this basket, right, the bigger the basket, higher the temperature. This solution can hold more solute. If additional solute is added to the solvent, it will dissolve until the solution is saturated. And that's what we saw when I was preparing this basket, right? I took individual markers and I kept slotting them in until it was finally saturated, finally full. All of this, I think, probably makes pretty solid sense, right? We've got a full bag, we got an empty bag. Put more in, can't put more in, pretty straightforward. Another example, you got sugar in an unsaturated sugar solution. The sugar will continue to dissolve until you reach the saturation point. Pretty straightforward. here's our third option, because I said there were three. And the fact that there are three here is weird. Like, there can be an empty bag, there can be a full bag, and then there's a third option, a supersaturated solution. What? What? How do we do that? This one is a bit tricky to show. I can't really show it with this. It won't work. A supersaturated solution is beyond full. It is more full than full. It holds more than the maximum amount of solute possible at a given temperature. So I'm going to put more than I normally can in the bag, right? So as we saw here, this particular basket here, I was able to stuff an extra 5 markers beyond the 5 that are in here, right? So we had 10 markers and an eraser in here. That is a saturated solution. If it was super saturated, that means that I would find some way to squeeze in one more marker. And that's weird, because it's like, but how would you do that? How do I put this in there? And what we have to remember is that it's not as simple as this analogy, right? It's not a container like this. This container is constantly changing in size. As I mentioned, I foreshadowed, the container will constantly change in size depending on the temperature. So let's take a look at what we mean here. This type of a solution is very unstable, and if you add just one solid crystal, solute will precipitate out of the solution. So it's like a carefully balanced teeter-totter or seesaw, whatever you want to call it, right? It's perfectly balanced, and if you so much as sneeze, it'll fall. You can prepare a supersaturated solution by first making a saturated solution with excess inside, then heat the solution until everything dissolves. What do I mean by that? Well, I told you guys, the basket here, the size of the basket is dependent on the temperature of the solution. If I make it warmer, the basket gets bigger. Well, what happens if I have a bigger basket and I stuff it full of markers and then I cool it down? Well, the basket starts to shrink, but it can't after a certain point, right? The basket will still have all those markers in it, and what can happen is you can get the perfect balance where the markers don't quite leave right away. They stay in the basket. They stay dissolved in solution. And the reason for this is just because, well, think back to physical properties of matter. I know it was a long time ago. Think back to it when we talked about the fact that in order for something to solidify, to turn into a solid, to become a solid, it needs to come together, right? This particle here is drifting around, minding its own business. This particle is drifting around, minding its own business. In order for them to become solid, they have to connect. Well, they have to actually get close to each other to do that. They can't be like socially distancing and they're connecting, right? Like, yeah, we're going to become solid now. They're too far away. They have to get close enough together to connect. So in order for that to occur, they need proximity. When the basket, in my analogy, when the basket is getting smaller, the markers are getting pushed closer and closer together. Eventually they might get close enough together that they start to interact, and then they start to turn solid. But that still requires a careful balancing point. Remember, we talked just a couple videos ago about the fact that in order for an ionic compound to be taken apart, what happens is that the water comes by, right, from the solid and grabs one and pulls it away. And then that one particle from the solid is surrounded by water. Well, when they're sitting in solution, they have to get close to each other, but they're both surrounded by water. So the water acts like a cushion. So not only do they have to get close to each other, but the water has to be removed from the situation so that way they can connect together. So if everything is just perfectly balanced, just perfect, it can sit there. Nothing will happen. But if you give it a shake, if you poke it, if you do anything, it will click together because the water will get knocked aside just long enough for everything to connect together. So there's a bunch of different things going on here, right? Proximity is one part of it. These things have to get close to each other. On top of that, you've got this whole temperature component. There's a lot going on here. So this third option is a strange one. When all the solute is dissolved, you slowly cool down the solution. In theory, as I just said, everything should precipitate out, but it won't right away because the water is in the way. When the solution reaches room temperature, or whatever temperature, it doesn't really matter, there will be more dissolved than was initially dissolved when the solution was saturated. AKA, I started off with 10 markers inside, I heated it up, making the container bigger, I stuffed in a whole bunch more markers, I cooled it down, the container should have gotten smaller, but it can't because there's all those markers in the inside. So it affects things. If you add a single solid crystal or tap the side of the container, the precipitation will occur. It's pretty crazy. Got a couple of videos here. To be honest, I put a link to this in the drive. I'm actually going to show you the first one just because it is pretty cool, which means, yes, you're now watching a video of somebody watching a video. It's a quick one, but I want to show it to highlight this, right? So I do recommend you load it up yourself. Here we go. No, we don't want that. We want this one. Okay, so this is another chap here. We got no sound today. Here he is. He's got a supersaturated solution, and he's going to be putting a crystal inside. So he's going to drop one in. So in here right now is more solute than there should be. The moment that there is a place for the solid to precipitate, the moment there's a place for the solid to connect, it does. And you can see right there on the surface, right? The crystals that are growing right now are coming from the solution. And the moment they had the opportunity to attach to this initial, we call it a nucleation site. The moment they had that opportunity, boom, they immediately start doing so. They just go nuts. And there it is. That is a supersaturated solution. It is unstable. It just took a single shake. To be honest, I'm surprised it didn't go off when the kids were bouncing against the table there. I know. A video. What can we do? These videos, these links are, of course, located in the plan. Take a look. See what you guys want to take a look at them. You can look through them a few more times. That's kind of it in terms of those things. Okay, so we've got a saturated solution, which is full. A supersaturated solution, which is more than full, and we have an unsaturated solution, which is not yet full. All of these, the last, like saturated and unsaturated, those two are easy. Supersaturated is the weird one. Notice the key is that whole temperature change, right? You needed to change the temperature. Okay, as you can see, that's it. It's a very short topic, right? It's just a 3-category thing. We're going to be using that to talk about different things, such as, for example, the solubility of gases. All right, but I'll leave that for next time. So I will see you guys then.